Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 5 for October 2022. Let us begin with the first question. Question 1. When copper is added to concentrated nitric acid, a brown gas is given off and the final solution is blue. In terms of oxidation number and electron transfer, how does nitrogen change in this reaction? In nitric acid we have HNO3, and the brown gas formed is going to be NO2. So the oxidation state is going to change from +5 to +4, and this is going to be reduction, which is similar to gaining electrons. So the oxidation number decreases and electron transfer is going to be gaining electrons, so the answer is going to be A. And in question 2, what is the pressure of hydrogen gas used in the standard hydrogen electrode? The pressure is going to be 100 kilopascals or 100,000 pascals, so the answer here should be a D. In question 3, an electrochemical cell is set up using the electrode system shown, which is that as well as that. They say what materials will be used for the electrodes in this cell. Now here we have 2 ions of chromium, and here we have 2 ions of titanium, so we need to use platinum for both. So the answer here should be a D. In part B, the reaction between dichromate and titanium-3 ions has E theta cell, which is that. The standard electrode potential for the dichromate chromium-3 electrode system is that. What is the standard electrode potential for that electrode system? Here I wrote the equations as below to show you how this could be carried out. So for this, it's going to be that. We are looking for that. We know for this reaction to occur, the E theta for the cell is going to be E right minus E left. But this is reduction, and that is oxidation. So this is going to be the E right, which is that. 1.33 minus the E theta for the left-hand half cell, which we do not know. And again, remember the one that gets oxidized is going to be on the left. The one that is reduced is going to be on the right. So making this the subject, I got 1.33 minus 1.14, giving me positive 0.19 volts. Therefore, C is my answer. Moving on. Question 4. The possibility of a reaction between potassium dichromate 6 and hydrochloric acid may be assessed using standard electrode potentials, but also depend on the activation energy of the reaction. So this is the general equation. They say when potassium dichromate 6 and hydrochloric acid are mixed, very little chlorine is formed under standard conditions, but a significant amount of chlorine is produced when concentrated hydrochloric acid is used. What is the effect on E cell and on EA of using concentrated hydrochloric acid? So using concentrated hydrochloric acid has no effect on activation energy because it does not change anything. But if you use concentrated hydrochloric acid, the E theta for the cell is going to be more positive. The equation is going to be towards the right. This should be equation, or the reaction goes more to the other side. So we're going to see a positive E theta for the cell. So this is going to be the answer. In question 5, the element zinc is not classified as a transition metal. This is because zinc is not a transition metal because it doesn't have stable ions with partially filled d orbitals. So the answer here is a C. The only stable zinc ion has the electronic configuration Ar3d10. In question 6, what is the electronic configuration of iron 2 plus ion? Remember, iron has 26 electrons, so we have argon 4s2 3d6. But iron 2 plus has lost the 2 electrons here, so it's going to be argon 3d6, which is going to be this as my answer. In question 7, platinum forms a complex with a formula that, which is used in cancer treatment. 3 possible structures of this complex are shown. The one used in cancer treatments is cisplatin only. So they ask the complex used in cancer treatments is, this is going to be X, which is cisplatin. So A is my answer. In question 8, when oxygen binds to the heme group of hemoglobin, each oxygen molecule, it bonds reversibly to an iron 2 ion. This is forming a dative covalent bond, so A is the answer. In question 9, the sequence shown is the mechanism for a reaction in aqueous solution. We can see all the steps. They say in the overall reaction, I try to cancel out similar things. That cancels out with that, this with that, and that with that. So adding up everything, I created that. We can conclude that silver acted as a catalyst, this silver one. The reason for that is because silver 1 was oxidized to silver 2 and then silver 2 was returned back to silver 1 at the end. So it did not participate in the overall reaction, but there was a conversion of oxidation state, an oxidation, and then a reduction. So silver 1 was the catalyst. So C is going to be my answer. Question 10. How many sigma bonds and pi bonds are there in a molecule of benzene? So in benzene, we have 3 pi bonds and we have 12 sigma bonds. So C is going to be my answer. Question 11. Benzene reacts with fuming sulfuric acid to form benzene sulfonic acid. Fuming sulfuric acid is concentrated sulfuric acid containing dissolved sulfur trioxide. So this is going to be the answer. Moving on. Question 12. The structure of the amino acid isoleucine is as shown here. What is the systemic name of isoleucine? We have 1, 2, 3, 4, 5. So there are 5 carbons in the main chain, which is going to be pentanoic acid because it's a carboxylic acid. But we have a methyl on carbon 3 and we have an amino on carbon 2. Of course, this is going to be carbon 1. So the name is going to be 2-amino 3-methyl pentanoic acid, and B is the answer. Next, they say, what is the structure of isoleucine in a solution of pH 2? This is in acidic conditions. Remember, this is isoleucine. In acidic conditions, this is going to be NH3+. So the possible answer is going to be that. The lone pair of electrons on the nitrogen is going to be donated to the H+ in the acidic condition, producing NH3. Moving on. Question 13. When dilute hydrochloric acid is added to butylamine and the solution is allowed to evaporate to dryness, a white solid forms. Of course, the white solid formed is going to be a salt. What is the formula of the white solid? The white solid is going to be that plus, remember there is a lone pair here, so the hydrogen is going to be received to produce NH3+, and then the Cl binds there. So it's going to be something like that. Let me put a plus here and a minus to show that this is going to be an ionic compound and therefore it's going to be a salt. So this is going to be the answer. Here the positive and minus are not put, but I put them here to show you that this comes here to create a plus here and the Cl binds, forming an ionic bond. In question 14, amines may be prepared by the reduction of nitriles. Identify the nitrile and the reducing agent used to prepare butylamine. So the nitrile is going to be this, and the reducing agent is going to be LiAlH4 in dry ether, which is that and that. So C is our answer. In question 15, the structure of crotonamide is as shown. What is the repeat unit of the polymer formed from crotonamide? The repeat unit is going to be similar to that, but with extensions like this. So A is going to be our answer. Question 16, the structure of a hydrocarbon is shown, which is that. They say how many peaks will there be in a carbon-13 NMR spectrum of this compound? The peaks are going to be 1, 2, these are identical, then those are identical 3, and those are identical 4. So there are going to be 4 peaks. Moving on. In question 17, the structures of cocaine and its metabolite are shown. So they say, how would you expect the solubility of cocaine in water and the pH of its aqueous solution to compare with that of benzoyl cognine? This is a carboxylic acid, but this has an ester group. So solubility in water cocaine is going to be less soluble in comparison to that. Cocaine is going to have a higher pH because this is a carboxylic acid. The hydrogen can be released and it's going to lower the pH. So the answer here is going to be a C. Moving on. Question 18. The use of recrystallization to purify a chemical compound depends on how its solubility in the chosen solvent varies with temperature. How should the solubility of a chemical compound depend on temperature? At high temperature, it has to be soluble, and at lower temperature, it has to be insoluble so that recrystallization can be carried out smoothly. So this brings us to the end of section A. Let's continue to section B. Question 19. This question is about the chemistry of vanadium. The standard electrode potentials of some vanadium species are shown. So we have these electrode systems. Explain the highest stable oxidation state formed by vanadium by referring to its electronic configuration. Vanadium is going to be argon, 3d3, and 4s2. So vanadium, of course, is going to have free and paired d electrons, and 2 electrons that are paired in the 4s. So there is a possibility of forming +5 oxidation state. So I said vanadium had 3 unpaired 3d electrons and 2 electrons in the 4s orbital. The sum of 3d and 4s electrons gives the highest stable oxidation state of +5. Moving on. In part B, a student suggests that iron VO2 may be converted into V3 using sodium thiosulfate with no other vanadium species being formed by reduction. Justify the use of sodium thiosulfate for this reaction by writing the relevant equations and calculating their Edexcel values. Use the standard electrode potentials given in the table and values from your data booklet. State symbols are not required. Here I refer to the data booklet and I got some equations. Now some of these equations I got from the table here, like for vanadium, so I used this here, and then for the thiosulfate I went to the data booklet. So this equation is converting vanadium 4 to vanadium 3, which is from the table, and the E theta value of 0.34 is here. So this equation is from your data booklet on page 10, and it's equation 12, but I have reversed it. Instead of writing it as a reduction equation, I have written it as an oxidation equation so that I can be able to write the overall redox equation quite easily. So this is going to be reduced and that is going to be oxidized. So combining the two, I had to multiply by 2 here to make these electrons 2 as well, since this has 2 electrons. So combining, I get the overall equation. And the E theta for the cell is going to be E right minus E left. Remember, on the right side, we have what is being reduced. So since this is a reduction equation, this is going to be to the right. And this is oxidation, this is going to be to the left. So 0.34 minus 0.09, I got positive 0.25 volts. And this reaction is feasible. So thiosulfate is a suitable reducing agent for the conversion of vanadium 4 to vanadium 3. But the question said with no other vanadium species being formed, so we have to find out if there is a possibility of the formed vanadium 3 to be converted to vanadium 2. So I used vanadium 3 to vanadium 2 from the table, and again the equation for thiosulfate from the data booklet. This is 0.09 volts, and this is from the table, negative 0.26 volts. And again, I multiply by 2 to make the electrons 2 here as they are here, and combine to make the overall equation, which is that. The E theta for that cell is going to be E right minus E left. We know this is going to be on the right, and that is going to be on the left. So combining the two, I got negative 0.35 volts. So we can say this is negative, meaning vanadium 3 will not be converted to vanadium 2 in the presence of thiosulfate. So this is proof that when we use thiosulfate with vanadium 4, vanadium 3 is the only product of vanadium that is going to be formed, and no other reduced version of vanadium is going to be formed. So my conclusion was, since E theta for the conversion to vanadium 3 is positive, then vanadium 4 will be converted to vanadium 3, but vanadium 3 will not be converted to vanadium 2, since the E theta value for that is going to be negative. Next they say, explain why nickel is not a suitable reagent to convert vanadium 4 to vanadium 3 with no other vanadium species being formed. Again, I went to the data booklet, got the equation for nickel. This is on page 10, and it's equation 10 but in a reversed order so that I can be able to write my equations easily. So I got that, which is for nickel, and this, which is for vanadium 4 to vanadium 3. We can see this is negative 0.25 and that is 0.34. So this is right and that is left. So the first reduction, vanadium 4 to vanadium 3, is going to be feasible since the E theta is going to be 0.59. That minus that gives us that. Now the second reduction, which is for that and that, if this is going this way, this is going to be to the right, which is negative 0.26 minus negative 0.25 volts. So the answer is going to be negative 0.01 volts. Now this value is very close to 0. So here, even though E theta is negative, there is a chance some of this vanadium is going to be converted to vanadium 2. So I said even though E theta is negative, some reduction will occur. And again, to explain that further, we can see this value is so close to 0. There is a chance that a little conversion of vanadium 3 to vanadium 2 could occur. Moving on. Here they say most vanadium produced is used to make a steel alloy called ferrovanadium. The vanadium content of ferrovanadium may be determined by a titration method. So the procedure is the sample ferrovanadium is dissolved in chloric 5 acid. The vanadium species formed is going to be that. Then the resulting solution is transferred to a 250 centimeters cube volumetric flask, washings added, and the solution made up to the mark with distilled water and mixed. Using a pipette, 25 centimeters cubed of solution is transferred to a conical flask, and 25 centimeters cubed of 0.25 mole per decimeter cube solution of iron 2 sulfate is added. The iron 2 ions react with these vanadium ions. So they've given us this equation, and then they say the resulting solution is titrated against potassium manganate 7 to determine the amount of iron 2 ions remaining. Again, for that, this is the equation. They say in an experiment, the mass of ferrovanadium used was 4.87 grams. The concentration of potassium manganate 7 was 0.0195 mole per decimeter cubed, and the mean titer of 22.50 centimeters cubed was obtained. They say give the color of the solution at the end point of the titration. The color of the solution is going to be pale pink. Remember, everything else is in less concentration, so it's going to be colorless, but the pale pink is due to the addition of an extra drop of manganate. Suggest why vanadium 4 ions formed do not affect the titration. In this titration, because the electrode potential of manganate 7 is higher than that of vanadium 4, manganate 7 should react with vanadium 4 for manganate 7 to be reduced and vanadium 4 to be oxidized. So according to the question, they say it does not affect the titration, meaning this reaction does not occur. So if this reaction does not occur, it means either the activation energy for that reaction is quite high, or the conditions are not standard conditions. Because if it's standard conditions, then this reaction is supposed to occur, and then the oxidation of vanadium 4 should occur to form vanadium 5. So here I said, the standard electrode potential of manganate 7 ions is more positive than that of vanadium 4, so vanadium 4 should be oxidized to use up the manganate 7. If it does not affect the titration, then the rate of the reaction is too slow, or activation energy is high, or the reaction could be carried out at non-standard conditions. So here they say calculate the percentage by mass of vanadium in ferrovanadium. So here I first wrote the equation and wrote the components that were given to us. So the information for magnet is provided. So moles of magnet used are going to be concentration times volume, giving us that concentration, and that volume here converted to decimeters, giving us those moles. This is excess iron from the previous equation. So moles of excess iron are going to be, the mole ratio is 1 to 5, so they're going to be 5 times the moles of manganate, giving us that. We were also given information about the initial number of moles of iron. If I take you back, remember they said in the conical flask we had 25 centimeters cubed of 0.25 mole per decimeter cubed. So it means number of moles are going to be concentration times volume, which is 0.25 times 25 over 1000, giving us these moles in the conical flask. The moles of iron 2 plus that reacted with this are going to be the initial moles, which are that, minus the excess moles, which gives us 4.05625 times 10 power negative 3 mole. So we go back to the equation and we can see the mole ratio is going to be 1 to 1. So that means the moles of iron are going to equal to the moles of this in the 25, which is that. So the moles of this in the 250 are going to be that times 10, giving us that. 1 mole of that contains 1 mole of vanadium. So it means the number of moles of vanadium are exactly that in the 250. So the mass of vanadium is number of moles times atomic mass, which is that, times the atomic mass, giving us that. So this is going to be the mass. So percentage by mass should be the mass of vanadium divided by the mass of the total sample given to us as 4.87 grams. So the percentage by mass is going to be the mass which we have here divided by the original mass times 100, giving us 42.4% to 3 significant figures. In part D, in the manufacture of sulfuric acid, vanadium 5 oxide, which is the catalyst used in the conversion of sulfur dioxide to sulfur trioxide, the equation is that. They say write 2 equations to show a possible mechanism for this reaction. State symbols are now required. In this reaction, sulfur dioxide is converted to sulfur trioxide by reacting with vanadium 5, and the vanadium 5 is going to be reduced to vanadium 4. And then vanadium 4 will react with oxygen so that it is oxidized back to vanadium 5. So this brings us to the end of question 19. Let's continue to question 20. Question 20. Delocalized electron systems are important in determining the chemical properties of some compounds. Compare and contrast the chemical reactions of bromine with benzene and cyclohexene And with benzene and phenol, by considering the effects of delocalized electrons, detailed descriptions of the bonds or the reaction mechanisms involved are not required. So here we have to compare benzene, cyclohexene, benzene phenol, and bromine. So here they are. Both benzene and cyclohexene have pi electrons that attract electrophiles. That is true, so they're going to react with electrophiles. But the delocalized electron cloud in benzene is more stable, while cyclohexene has no delocalization. Benzene undergoes through electrophilic substitution reactions, while cyclohexene undergoes through electrophilic addition reactions. Both benzene and phenol have delocalized electrons, so they undergo through electrophilic substitution reactions. In a similar manner, benzene forms bromobenzene, and phenol can form 2,4,6-tribromophenol. Also in phenol, the lone pair of electrons on the oxygen atom interacts with the delocalized pi electrons, making phenol to react with electrophiles under milder conditions than benzene. So this brings us to the end of question 20. Let's continue to question 21. Question 21. Quinine is a toxic compound present in poison hemlock. The structure of quinine is shown, with R representing an alkyl group. This is quinine. A sample of 0.235 grams of quinine was vaporized at 185 degrees Celsius and this pressure. The volume of the vapor was 67.1 centimeters cubed. Show by calculation that the molar mass of quinine is that. So here the mass is that. The temperature given is in degrees Celsius, so you add 273 to create that. The pressure is 105,000 pascals, so conversion of this to Kelvin gives you 1 mark. Conversion of volume to meters cubed also gives you a mark. So using PV is equal to nRT, number of moles is going to be PV over RT. So substitute pressure, volume, temperature, and R. I got that. We know number of moles is mass over molar mass. So molar mass is equal to mass divided by number of moles, which is going to be the mass given here divided by the number of moles calculated here, which is approximately 127 gram per mole. Next they say, deduce the molecular formula of the alkyl group R using the structure of quinine and its molar mass. You must show your working clearly. Quinine is carbon 5, hydrogen 10 in R. So 127, which is the molar mass of that, is going to equal to 12 times 5 plus 1 times 10 plus nitrogen, which is 14 plus R. And when you make R the subject by subtracting 127 minus the rest, I got R is equal to 43. So possible structures of R, because 43, that is alkyl, could be that or that. So this could be C3H7 if you're writing the molecular formula of R, which is that. Moving on. In part B, the table summarizes the low-resolution proton NMR data for the R group in quinine. So this is the information given to us. They say explain why only one of the two possible structure formula of R can give this data. So if we have 3 proton environments and the possible structures are that and that, it cannot be this because this is going to have one environment and these two are identical, so that is out. So this data here means this is going to be the structure we're looking for with 3 different proton environments. So I say the structure of R is that because it has 3 proton environments. CH3 has only 2 proton environments since the CH3s are identical. Here they say in the high-resolution proton NMR data for the R group in quinine, the peak for proton environment 2 is a sextet. They use a splitting pattern for proton environment 1 and 3 using the information in the table. So I drew the possible structure, which is this. This is the one that is going to be a sextet because we see 3 hydrogens here and 2 hydrogens here. So 5 plus 1 creates a 6. So these protons are the sextet. So if this is 2, this is going to be 1, which is surrounded by 2 hydrogens. So 2 plus 1 is going to be 3, which is a triplet. So environment 1 is a triplet. In this environment here, we have this carbon that has 2, and we have this carbon that has 1. So that is 3. 3 plus 1 gives us 4. So these protons are going to be quartet. So here I said environment 1 is a triplet, 2 protons on the adjacent carbon. So 2 plus 1 is equal to 3. This is using the n plus 1 rule. And environment 3 is a quartet, 3 protons on the adjacent carbons. So 3 plus 1, this is the n plus 1 rule, gives us a 4, meaning quartet. In part C, explain using a diagram which type of stereoisomerism is shown by conine. In your diagram, use R to represent the alkyl group. If I put R here, this carbon contains 4 different groups, and that means this is a chiral center. So I say the isomerism is going to be optical isomerism because an asymmetric carbon or chiral center exists in conine. Conine is a non-superimposable mirror image. So this brings us to the end of question 21. Let's continue to question 22. Question 22. Many oxides of transition metals are used as colored pigments. Viridian is a blue-green pigment with a formula that M is not the symbol of an element. When a sample of viridian is heated until all the water crystallization is removed, the mass is reduced by 19.15%. Identify element M. I wrote the equation for the decomposition. That decomposes to give us that and that if all the water is removed. The decrease is going to be due to loss of water. And remember, the mass is reduced by 19.15. So 19.15 divided by 100 of the total is going to equal to the water lost. Since each water is 18 times 2 is 36. So the total is going to be 36 times 100 divided by 19.15, giving me 187.98 gram per mole as the molar mass of the whole thing. So my next step is to get this minus the component of 2 water molecules and the component of 3 oxygen atoms. That will give me M2, and then when I divide my answer by 2, it will give me the component of M. So this is what I did here, and M came out as 51.99, which is approximately 52, and therefore M is going to be chromium. In part B, cobalt 2 oxide is used in the ceramic industry as an additive to produce blue glazes and enamels. Cobalt 2 oxide dissolves in sulfuric acid to give a pink aqueous solution of cobalt 2 sulfate. When concentrated hydrochloric acid is added to aqueous cobalt 2 sulfate, a dark blue solution forms. Name the type of reaction that occurs when concentrated hydrochloric acid is added to aqueous cobalt 2 sulfate. This is a ligand exchange reaction. The next, write an ionic equation for the reaction that occurs when concentrated hydrochloric acid is added to aqueous cobalt 2 sulfate. State symbols are not required. Because the cobalt 2 sulfate is aqueous, the cobalt 2 is going to be surrounded by water ligands as we see here. Then adding concentrated hydrochloric acid is going to be 4Cl-. Remember, chloride ligands are going to form tetrahedral complexes. So this is going to be, that is the product, and then that. The charge is -2 because cobalt is 2+, and each of the chloride is going to be -1. So here we have a 2- charge. Next they say, explain why the shape of the complex ion changes when concentrated hydrochloric acid is added. In the water ligand, the oxygen atom of water forms a dative covalent bond with a cobalt. Since oxygen atoms are smaller, 6 of them can surround the cobalt, but the chloride ligands are bigger, so only 4 can fit around the cobalt. So here I said, the hexa-aqua complex is octahedral. Since oxygen atoms are small, more can form dative covalent bonds with a cobalt 2. However, chloride ions are bigger in size, so only 4 can form dative covalent bonds with cobalt 2, resulting in a tetrahedral complex. So this brings us to the end of section B. Let's continue to section C. Question 23. Plants are a rich source of useful chemicals, although their applications have often predated the identification of the active compounds. One of the best known examples of this is the use of willow bark extract to reduce pain and fevers, a practice that is at least 2,000 years old. The active compound in willow bark is salicin, and we are given salicin here. They say in the body, salicin is changed into salicylaldehyde and then salicylic acid. Salicylic acid may in turn be converted into 2-acetoxy-benzene carboxylic acid, a compound which is better known as aspirin, one of the most widely used medications in the world. So they say calculate the percentage composition by mass of the elements in salicin. Salicin has 13 carbons, 18 hydrogens, and 7 oxygens. The molar mass is 13 times 12, 18 times 1, and 7 times 16, which is equal to that. The percentage by mass of carbon is going to be 13 times 12 divided by that times 100, giving us that. Percentage by mass of hydrogen, they're going to be 18 divided by 286 times 100, giving us that. And the percentage by mass of oxygen is going to be 7 times 16, which is that, divided by 286 times 100, which is that. In part B, the first stage in the breakdown of salicine results in the formation of salicyl alcohol, which is this one here. They say salicyl alcohol is readily oxidized in the laboratory to form salicylic acid. State the reagents and the conditions needed for this oxidation. This is an alcohol that is going to be converted to a carboxylic acid. So oxidation, we're going to use potassium dichromate, and the conditions are going to be sulfuric acid as a catalyst, and you heat under reflux. Here they say the boiling temperature of salicyl aldehyde is 197 degrees Celsius. Suggests why this makes it very difficult to obtain salicyl aldehyde by oxidizing salicyl alcohol, because the aldehyde will need to be distilled or from a reaction mixture to prevent further oxidation, so this is going to be quite hard. In part C, aromatic aldehydes such as salicyl aldehyde may be prepared in the laboratory by electrophilic substitution. For example, benzaldehyde may be obtained by reacting benzene with a mixture of carbon monoxide and hydrogen chloride in the presence of aluminium chloride. The mixture of carbon monoxide and hydrogen chloride reacts like methanol chloride. Write an equation for the formation of the electrophile from methanol chloride and use displayed formulae. So this is methanol chloride, and that is aluminium chloride. The chloride is going to be taken away by a halogen carrier to create that, and this is going to be left as the electrophile. Draw the mechanism for the formation of benzaldehyde from benzene using the electrophile from C. So this begins with a ring donating electrons to the electrophile here, which is that, forming a partial ring with a positive inside and the hydrogen displayed out. In the next step, the bond breaks, the carbon-hydrogen bond, returning the electrons to the ring, and then the ring is reformed and the hydrogen is going to be released. So part D, salicyl aldehyde may be used in the synthesis of coumarin, a compound which occurs in many plants. Coumarin is in turn used to prepare warfarin, a compound prescribed to reduce blood clotting. So this is coumarin. One suggested synthesis of coumarin from salicyl aldehyde involves the formation of an intermediate compound F. So we have salicyl aldehyde and compound F. They say divides a synthesis of F using salicyl aldehyde and bromoethane as the only organic starting material. Include any other reagents and intermediate compounds and give essential reaction conditions. I began by using Grignard's reagent, and then I'll introduce this a little bit later. So to create that. So CH3CH2Br with magnesium and dry ether, I created my Grignard's reagent. Then this Grignard's reagent is going to react with that. Remember, this is an aldehyde and Grignard's reagent, so I will produce a secondary alcohol. The intention is to produce a secondary alcohol here and then convert it to an alkene. So this is the secondary alcohol. And then in the last step, I went through dehydration to remove water using concentrated phosphoric acid. This is going to break away and one hydrogen here, creating a double bond here, and that is my product. In part E, salicyl aldehyde combines with 1,2-diaminoethane in the condensation reaction to form saline ligand, which is that. Saline ligand reacts with many metal ions to form very stable complexes, which are useful catalysts. Draw a diagram of the complex that one saline ligand forms with Nico2 plus ion, showing the type of bonding involved. So this is the ligand. We can see this nitrogen, that nitrogen, the oxygen and the oxygen are going to participate in the formation of dative covalent bonds around the Nico. So the possible is going to be that, and that, forming for dative covalent bonds, and this is going to be your structure. Lastly, here they say, explain why the saline ligand complex of Nico2 plus ion is much more stable than the aqua complex of the same ion. So it's going to be more stable because remember, as this one reacts, more dative covalent bonds are going to be formed, and the product side is going to have so many more particles, meaning the entropy is going to increase. So I said, when the saline ligand complex is formed from the aqua complex, more particles are formed, so the entropy of the system increases. And again, in this case, water ligands are going to be replaced, so meaning more water products are going to be formed, and that creates more disorder or more particles, so the entropy increases. So this brings us to the end of question 23. as well as to the end of this paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.